Hey guys, so in the last lecture, we have seen the definition of logarithmic decrement, and also we have seen the formulas for logarithmic decrement. Two formulas we have seen, one with respect to the ratio of the first and the last amplitude or any amplitude, and another with respect to damping factor. And also we have seen few examples of that, so similar examples can be asked in exam. So now today we are going to start a new topic, that is torsional vibrations. So what is torsional vibration? So we have discussed this in classification of vibration. So when a particle of the spring or a disk moves in a circular manner about the axis of the spring, then it is known as torsional vibration. So what does it mean? Suppose there is a spring mass system. So if this disk, so this is a mass, this mass is a disk suppose, and it's suppose top view is circular, if we can see here. uh, so, so this is circular. So suppose I am twisting this spring in this direction and then leaving it. So what will happen is that, so it will be twisted, so in this direction, and if I leave, then it will automatically untwist in this direction, and then again twist in this direction, and then again it will twist and untwist in circular manner. So what will happen, suppose uh, suppose it is moving. So this circular disc is moving. Suppose I am twisting in this direction. So suppose this disc is moving from, so suppose this is the mean position, and it is getting twisted up to A. So this is moving A, then it is going back to mean position, and then it is again twisting in C position. So A and C are extreme positions. So A and C are extreme positions, and B is mean position. B is mean position. So when the so this is when this particle is moving in a circular manner with respect to the axis of the spring. It is known as torsional vibration. Now the spring is twisted and untwisted alternatively. So torsional shear stress is induced in this. So here torsional shear stress is induced. So so our formula for just linear vibration was like this, that x double dot plus k by m, x is equal to 0, as we know that for this is for linear vibration. Now here in circular motion, uh, instead of distance, because here instead of distance it is rotating, so here it will be an angle, so that angle will be theta. So this is acceleration, so angular acceleration will be theta double dot. So here it will be theta double dot, and instead of mass we use here moment of inertia I. Instead of x, theta equal to 0, and what instead of k, what it will be, so here this will be k, we will use kt. So kt is suppose torsional stiffness, so here we will use kt as torsional stiffness. So what is I? So I is mass moment of inertia, theta is angular twist or angle, and theta double is angular acceleration. So this is the formula for this twist torsional vibration. So similarly, if we compare with an SHM equation, so if we compare this with SHM equation, so what we will get? We will get natural frequency omega n is equal to under root kt by I. So this is the natural frequency of this rotor system. Now the equation for we will discuss equation for different types of rotor system. So we will see for different types of rotor system. So we will see single rotor, double rotor, and three rotor system. So we will start with uh, equation of torsion for single rotor system. So suppose this is a fixed support and it is having an this similar to suppose a cantilever beam. So this is suppose a rotor having moment of inertia I. It is at a distance L from the fixed support and it is connected to this fixed support uh, with the help of a shaft. So now this is the rotor which is rotating. So now we will use the equation that is T by J is equal to G theta by L is equal to tau by R to find the torsion in this of the rotor. So as we know that what that KT is equal to, what is KT? So this is rotary stiffness. So in linear stiffness, as we know, F is equal to kx. So k is equal to F by x. So similarly here, kt will be equal to, instead of force, this will be torque. Instead of distance, there will be angle theta. So kt is equal to t by theta. So if I want to find t by theta, by using these two equations, so what I will get, so theta if I bring here and j on the right side, so I will get gj by L. So gj by L. So now if I want to find omega n, so what is omega n? So here it is written omega n is kt by I. So I will just use that equation. So under root kt, so kt is gj by L and I. So our natural frequency for single rotor system is Gj by IL under root. So this is the equation for single rotor system. Now we will see for two rotor system and also then for three rotor system. So let's see for two rotor system. So two rotor system. So suppose there are two rotors. Rotor A and rotor B. So and a shaft is connected having a diameter small d. Now the moment of inertia of rotor A is suppose Ia and for rotor B is Ib. And uh, now what is the possibility of these rotors? So first possibility of rotation is that both rotors moving in same direction. So both rotors moving in same direction. What does it mean? So if both rotors are moving in clockwise direction or anti-clockwise direction, so in that case, so no vibration or phase difference can occur. So when vibration will occur, so when uh, both rotors rotates in mutually opposite direction. So what does it mean? That if rotor A is moving clockwise, so B will move anti-clockwise, and if B is moving clockwise, so A will move anti-clockwise. So if both the rotors always rotate in mutually opposite direction, then we can have a twist here. So then we can have the twisting of the shaft, and we can have a center point where uh, there will be a node. So what do you mean by node? So if it is getting twisted, suppose this is moving in this direction and this is moving in this direction, so there will be a twisting. So there will be a point on the shaft which will be in its position to the central axis of the original shaft axis. What does it mean? So means that this point has not been moved due to this twisting. So it is at its original place only. So that point is called node. So that is an important node. So we will see in three rotor system also that similar nodes we can achieve. So if what will be the if this distance from the node to the left rotor is LA, so length is LA, and to the right rotor is LB. Suppose now we are not saying here till now that LA is equal to LB. If this is at the center, that is IA is equal to IB, then only LA will be equal to LB. If these are both equal, then L equal to LB is possible, and this can come at the center. But what I'm saying here now it is that we will use, as this two rotor is on the same shaft, so it will experience the same vibration and will have the same natural frequency. So what does it mean? Uh, so omega n1 will be equal to omega n2. So this section in the shaft which does not undergo any twist is known as nodal section. This is a definition, and that point is called node. Okay, now here the natural frequency of both will be same. So what is the natural frequency? So here we have natural frequency formula, that is Gj by IL. So if I write under root Gj by IL equal to under root Gj by IL. Now here it is 1 and here it is 2. So J, what is J? J is polar moment of inertia, which is having the formula of J, pi by 32 d raised to 4. Here as the shaft diameter is similar, so J will be equal. So I don't have to write 1 and 2. And next, what is G? So G is modulus of elasticity, so which is also same. So here we have IA, and here we have IB, and similarly we have LA, and here we have LB. So from this equation we got, if we get cancel out everything, so we'll get IA LA is equal to IB LB. So if IA and IB are same, then we can say LA and LB will be same. So this result we have obtained. So L equivalent, so total length will be equal to LA plus LB. So this is the free torsional vibration of a two rotor system. Now we will see another uh, theory, that is torsionally equivalent shaft. So torsionally equivalent shaft. So torsionally equivalent shaft means, so suppose there are two rotors. So let's say rotor A and rotor B. But here, as we have seen in previous case, the diameter of the rotor was same. But if there are three different diameters of the rotors, so suppose it is D1, D2 and D3. So two rotors A and B connected with the three different diameters of the shaft. Now if I want to find an equivalent shaft diameter with which I can replace these three diameter and just use a single diameter, so what it will be the length of that diameter, that shaft, sorry. So suppose here the angle of twist, so that is theta, here will be different, so total angle of twist will be theta 1 plus theta 2 plus theta 3. So now we will use this formula as T by J is equal to G theta by L. So in this I will make theta as a subject, so what I will get as theta, so theta will be equal to TL by GJ, so theta equal to TL by GJ. So if I use this equation here, so what I will get, first which terms will change and which terms will not change, so we have to see that also. So first I will just write it down that TL by GJ is equal to T1 L1 by GJ1 G1 G plus T2 L2 by GJ2 plus T3 L3 by GJ3. Now in the last case, we have taken G and J as same, but here we will not take G and J as same because the diameter is different here. So as J is polar moment of inertia, which formula is directly dependent on the diameter, so J we will not take same. Now what we will take same here, so we can take G as same modulus of elasticity, and the torsion in the each and every diameter will be same. So G and T are same here, so T and G will get cancelled out, so what we are left with is L by J is equal to L1 by J1 plus L2 by J2 plus L3 by J3. Now what is the formula for J? J formula is polar moment of inertia, that is J is equal to pi by 32 d raised to 4. So this is the formula for polar moment of inertia. So this formula we will use here. So we'll get L by pi by 32 d raised to 4 is equal to L1 by pi by 32 d1 raised to 4 plus L2 by pi by 32 d2 raised to 4 plus L3 by pi by 32 d3 raised to 4. So here pi by 32 will get cancelled out. So we are left with L by d raised to 4 is equal to L1 by d1 raised to 4 plus L2 by d2 raised to 4 plus L3 by d3 raised to 4. So this is the formula for torsional equivalent shaft to find the length of the equivalent shaft. Now if I will say that the shaft which I required equivalent shaft, so instead of that this all three shaft, if I have just one shaft here, so if that diameter, if I'm taking as the initial diameter d1, so what I will get, so suppose I'm taking, if d is equal to d1, if I'm assuming that, so what will happen, and this d1 I'm multiplying on the right hand side, so L is equal to L1 plus d1 raised to 4 and d1 raised to 4 will get cancelled plus L2 upon d1 upon d2 raised to 4 plus L3 into d1 upon d3 raised to 4 and so on. So here d1 will come as a common, so this will be the length of the diameter, length of the equivalent shaft if it is having the diameter as the diameter of the first shaft. So this is the equivalent shaft diameter example. So we will see few rotor equations and examples also. So now in next lecture we will see three rotor system. So here what we have seen today, so today we have seen torsional vibration, its equation. So what's this equation? Rotary motion. Then we have seen a single rotor system. So with the help of single rotor system, we have found the natural frequency of the single rotor system. Then we have derived two rotor system. So in that we have got an equation of the length, that is LA upon LB, and we have introduced this node, that when vibration will occur, the node will occur. Then torsional equivalent shaft, that is if the diameter are different at that time, what will be the length of diameter of the equivalent shaft having a single diameter, that if we take as a d1. So this three concept we have seen today. So that is single rotor system, two rotor system, and equivalent valent shaft in two rotor system of different diameter. And before that, we have seen torsional vibration equation. So torsional vibration. So this topics we have seen today. We will see example also, and in next lecture uh, we will see a three rotor system. So we'll see three rotor system. So 1, 2 we have seen three rotor system, and also we'll see examples, few examples for 1, 2 rotor equivalent shaft diameter and three rotor systems. This systems examples we'll see. So hope you understood this lecture, and hope to see you in the next lecture. So thank you very much.